So here's lesson 2 on scientific notation and metric conversions, two things that we're going to use a lot in our study of physics. To begin with, scientific notation is important because physicists frequently deal with very large or very small numbers. So good examples of this are Avogadro's number, and if you've taken chemistry at the introductory level, you'll know that Avogadro's number expresses the number of particles in a mole of a substance, and that's 6.022 times 10 to the 23rd. So that's 6.022 and then a whole bunch of zeros after it. Planck's constant, on the other hand, which is used quite a bit in quantum mechanics, is 6.626 times 10 to the minus 34, so a very, very tiny number. Scientific notation then is a time-saving process that's used to represent large and small numbers, and it's something that we're going to work with quite a bit. So there's some specific rules that we use for writing scientific notation. The first digit is a number from 1 to 9. After that digit, a decimal point, and then the rest of the digits follow. Okay, so it's one number, a decimal point, and then the rest of your figures. This number then is multiplied by some appropriate power of 10. So in the example here, we're going to write the following measurements in scientific notation. 4.250 meters can be expressed in terms of scientific notation. And what we're going to do is move that decimal spot 3 places to the left. And by moving it 3 places to the left, we increase by a power of 10 every single time. So this number becomes, after we move the 3 spots, this number becomes 4.250 times 10 to the 3 meters. You'll notice that by moving the decimal place, we haven't affected the number of significant figures, and we shouldn't. Just because we write it in scientific notation, significant figures stay the same. 0.000980 moves the decimal place 4 spots, but this time to the right. And when we move a decimal spot 4 times to the right, for each step we take, we multiply by a negative power of 10. So this becomes 9.80 times 10 to the minus 4. So just to reiterate, we must monitor significant figures when we're writing things in scientific notation. So pay attention to the rules for multiplication, division, and addition and subtraction. One thing that's really important that students often ask when they're starting to get comfortable with significant figures in scientific notation is that the power of 10 is not included in our count for significant figures. So the times 10 to the power of 3, that is not considered any type of significant figure at all. It's just kind of left on its own. Here's another example where we're going to use scientific notation in our calculators. And you may want to take a note because all of this stuff should be done with your calculator, and I'll kind of take you through how we do this. So we definitely want to use our calculator. Entering 4.02 times 10 to the minus 23, we actually don't have to type in times 10 to the power of negative 23. You can, but most calculators have a button to help us with that. Okay, so here's what you would enter. You'd enter 4.02 as normal. And then there is a button that you would have on your calculator. Sometimes it's expressed as the capital letters EXP. Sometimes it's 2 capital E's. Sometimes it's a capital E and a small xp. Sometimes it says times 10. Look for this button on your calculator, and if you're not sure, ask your physics teacher or ask your math teacher to get you to find out where that button is, because it will save you time. Then the way that you enter the exponent is you press, say in this example, the negative sign and then 23. So here, if we do this calculation, we would say that this comes out to 2.1708 times 10 to the minus 17. We need to look at significant figures. Each of these, we would say, has 3. If we're keeping track of the 5.40, that would be another significant figure. So we have to truncate this, and so we write this as 2.17 times 10 to the minus 17. In example B, we have 6.7 times 10 to the 28, and we're dividing by 3.143 times 10 to the minus 7. So this calculator, this in your calculator, what it should give you if you're doing this along with me is 2.13172 times 10 to the 35. And of course, what you do is you'd say, okay, well, there's two significant figures in the first digit, so we want to round this off after two significant figures, and we'd keep 2.1 times 10 to the 35. When we're looking at metric conversions, we need to know how to convert metric units very quickly and very easily. And it's actually not that tough to do. The following is a memory aid that might be useful, and I've put it in the notes so that you can use it and you can refer to it. But in general, I tell my students that you need to know anything from giga all the way down to nano. And the reason that you have to know these is because we're going to use them a lot. So I would say memorize those numbers. The other ones, the ones that are very, very big and the ones that are very, very small, you may need to look up from time to time. Most of the time these are in textbooks. But in general, the most common ones, anything from giga to nano, you really should commit to memory and you should know, okay, this is how I convert back and forth. There's no need necessarily to memorize anything. Dimensional analysis is a really good way to convert between units because you don't have to memorize a thing. So if we wanted to convert 300 milligrams into grams, we could say, all right, well, let's start with 300 milligrams, and we draw a little T-chart. We want, the thing with dimensional analysis is that we kind of want to treat units like they're variables so that we can cancel the top and cancel the bottom, or simplify the top and simplify the bottom. So if we want milligrams up top in the numerator to cancel out, then we got to put milligrams down below. And how many milligrams are in a gram? Well, there's 1,000 of them. And so we'd write 1,000 milligrams underneath, and we write 1 gram on top, symbolizing that there are 1,000 milligrams in 1 gram. What you'll notice now is that you've got the milligrams up top, the milligrams down below, and those units will simplify or cancel out, and then we can deal with the numbers. 300 divided by 1,000 is 0.3. Now you may be asking, holy cow, that's a lot of work. And it is a little bit more work, especially for something like this that's quite simple. However, when we get into trickier situations, like converting 3.8 times 10 to the minus 7 nanometers into gigameters, it might help. So let's begin by writing 3.8 times 10 to the negative 7 nanometers. And instead of going in one big jump, let's go from nanometers to convert it to meters, and then we'll go from meters and we'll convert it to gigameters. So here's the question. We want nanometers down below, and we know that in every single meter, there are 10 to the power of 9 nanometers. We got that from the chart. So now we've got nanometers, and we've canceled them with nanometers, and we have units of meters. And now we want to go from meters to gigameters. So we'll draw another line, and we'll notice, oh, there's 10 to the 9th meters in every gigameter. So meters cancels with meters, nanometers is canceled with nanometers. All that we're left with is gigameters, and we can now say 3.8 times 10 to the negative 7. We can divide by 10 to the 9th, and then divide by 10 to the 9th again, and we get 3.8 times 10 to the negative 25 gigameters. Where dimensional analysis becomes really important is when we're converting from something like meters per second into kilometers per hour. And so we're going to do this quite a bit. Here's the example. We've got 200 meters per second. So we got meters up top and we got seconds down below. Now, how many meters are in a kilometer? There are 1,000 of them. And again, that comes from the chart. So we've got, well, let's do time first. There's 60 seconds in 1 minute. So we put the 60 seconds up top because we want seconds to cancel with seconds, and the minutes down below. And how many minutes are in an hour? Well, we've got 60 of them, so there's 60 minutes in an hour. The minutes will cancel with the minutes. And now we can get rid of the meters. There's 1,000 meters in every kilometer. And if you look at what's left over here, you've got kilometers on top, and you've got hours on the bottom. And so when we go across and we multiply everything on top together, and then we divide by everything that's on the bottom, we get 200 times 60 times 60, all divided by 1,000, and we end up with 720 kilometers per hour.